We are going to look at simple manipulation of Newton's law, basically the second law. I'm going to introduce fundamental and derived units, what a Newton really is, the difference between weight, mass, force of gravity, and the mass equivalent of a force. That last bullet is really important for you to be able to grasp what a force really is in an intuitive way rather than just with mathematics. We're going to see if we're isolating ourselves to a single force that we don't require this summation notation or a little F net here, and the vector signs will be able to drop if I keep the problems in one dimension. The force of gravity is simply an alteration of Newton's second law to change the acceleration to that of the Earth. So textbooks might convince you it's a new rule. It isn't. If we write out the units of force, putting square brackets around all the items in an equation means I want you to tell me the units. We get kilograms times meters per second squared. We just say this kilogram meter per second squared. This is what a Newton is. I also want you to look at Newton's law from this perspective. Acceleration is force over mass. If I tell you the force in newtons and the mass in kilograms, you can write acceleration as newtons per kilogram, which is a little bit nicer than writing meters per second squared, particularly on a computer. But it's going to change the thoughts in your head as to what acceleration is. So I'm going to want you to freely change your viewpoint from meters per second squared to newtons per kilogram, and you will find it makes a huge difference in your understanding of a problem. Let's look at our fundamental versus derived units. You've already known D is for distance, M is for mass, T is for time, meters, kilograms, and seconds. There are others that are tangible quantities in our universe. We're all aware of distance, mass, and time, temperature, intensity of light, electric current. If you got a shock, the amount of substance will be done in chemistry, and it's called a mole. The purpose of a mole is it allows you to turn cups of sugar to like actual number of sugar molecules. You've learned a few derived units. You know speed is not a fundamental unit. It's meters per second. Density is kilograms per cubic centimeter. Okay, you've combined these units. Meters squared, meters cubed. But what we haven't done is given them a name. Can you imagine if your speedometer, instead of saying kilometers per hour, said Ford units? How many Ford units are we driving? You've been using derived units your whole life. You just didn't know you've been using them when they've been named. Example, voltage, after Alessandro Volta. Watt, after James Watt. Amperes. These are hiding fundamental units. So power is joules per second, and joules itself is not a fundamental unit. We start sneaking in bundles of units by giving them a name. And in terms of Newton's law, if I say what are the units of force, we get kilogram meter per second squared. By definition, that is a Newton. So when you see Newton, we expect you to be able to write out what it actually is hiding. It's hiding a kilogram meter per second squared. When you manipulate a formula, you need to be able to unpack the units and rearrange them. Did Newton discover force? Invent force? The conceptualizer of force? Did a Newton exist before he put it together? And he didn't call it after himself. Later people do that. Let's take an example with the 2019 Honda Odyssey, which has a curb weight of 2,026 kilograms. This vehicle can accelerate to highway speed in 7.6 seconds. What force must the drivetrain exert? Step 1, we have to calculate our acceleration in this problem. Since I told you the vehicle starts from rest, you don't need to do 30 meters a second minus 0. That's kind of implied. And we get an acceleration of 3.95 meters per second squared. We're all friends here, so we can substitute 4. Rounding severely again, I get 8,000 newtons. Our next step is to figure out if 8,000 newtons represents a lot. Well, it's enough to get a 2,000 kilogram minivan up to highway speed in 7 seconds. Force is a vector. It matters which way you push. Mass is not. Acceleration is a vector. So when we multiply acceleration by mass, we get a new vector. The acceleration due to gravity is 9.8 meters per second squared down. Square brackets and a D indicates down. I like to throw a vector sign on top of it just to be absolutely certain you know that's a direction. We write out Newton's law, and we take a look at the force on this weightlifter. If he picks up 100 kilograms and holds it stationary above his head against gravity, the force he would need to provide would be the 100 kilograms times the acceleration due to gravity, which is 980 kilograms meters per second squared. That is 980 newtons. You just bundle the kilogram meter per second squared into a newton. This means 100 kilograms weighs 980 newtons. So if you think you can fight a 1,000 newton force, you are telling me you are able to pick up 100 kilograms, rounding gravity to 10. Now you have the power to turn a newton into something more comprehensible. We'll look at the formula one more time so you can see this mess here. We have units, we have a direction, we can group the fundamental units into a derived unit called a newton. And I'm reminding you again, the triple bar equal sign means it's an identity, an equivalence, or a definition. Forces cause acceleration. Most people prefer Newton's law written as F equals ma. It is easier to look at. However, written this way, the equation is really saying forces are caused by mass and acceleration. And that is not true at all. What's really happening is the force acting on a mass is causing acceleration. That makes this rearrangement of the equation express the truth of nature more than this one. Either one can be committed to memory and rearrange it, but in physics, the rearrangement of an equation to put the letter you're solving for on the left side can actually make a conceptual difference in your head, something that doesn't happen in math class. So never say forces make things move. It's too vague. You say forces make things accelerate. Forces are invisible. They can be calculated. But mass and acceleration are both visible and observable. Well, it's kind of the same thing, right? You can make recordings on them. Now, forces you may feel with the human body if they're strong enough. So you can feel the effect of a force, but it is much easier to record the mass and acceleration and calculate the force. So this is the cause, and the effect is the acceleration. And the object is the m. Your weight and g-force as benchmarks. Imperial measurements didn't make a clear distinction between weight and mass. Metric does. Mass is a quantity of matter, while weight is the force of gravity on that matter. Somebody, sooner or later, is going to go into outer space, pick up a solid rock, and whip it at someone's head, going, "Hey, we're in 0G!" Boom! It's still going to split their skull open. It still has atoms in it. They don't go anywhere. The force of gravity on an object is by its very definition the weight of the object. They're the same thing. So you could write W equals mg. When you see FG, you think weight. So if you have a mass of 50 kilograms, what is your weight in metric? 500 newtons. This means anytime I give you a force, all you have to do to make it a mass equivalent is knock a 0 off of it, and it will now be in kilograms. Knocking a 0 off is divide by 10, or divide by 9.8 if you're nitpicky. At the start of this lesson, if I said, I'm going to hit you in the chest with 1,000 Newton force, you'd be like, I don't know if I'll feel that or not. Now, if this 1,000 Newton force is the equivalent of mass times gravity, we can pretend that this applied force came from a mass, and so we pretend it's weight. So we'll solve for the equivalent mass that would make this force. 1,000 Newton force hitting you in the chest, you divide by the acceleration due to gravity, would be the equivalent of 100 kilograms. That's a pretty hefty guy. Let's return to the Honda Odyssey situation and reimagine this problem. Could you exert enough force to stop a Honda Odyssey from accelerating? Could a strong man hold 8,000 newtons? Right now, with you just learning what a newton is, you wouldn't know the answer. But I said we can replace it with a mass equivalent. How much matter in kilograms would generate 8,000 newtons of force in a gravitational field like Earth? So we reimagine our situation slightly different. We're going to pretend that the force is from a mass in Earth's gravitational field. Or let's pretend it's a hella big weight. This is what we're going to imagine. How big would that mass be that would generate 8,000 newtons of pull on him, exactly like the Odyssey's engine could do? We know it's 8,000 newtons. We're going to put it in a gravitational field, and we want to know how many kilograms of mass would this be. So we take Newton's law, except in this case it's now weight in a gravitational field. So we solve for mass, and 8,000 Newton force in the 9.8 meters per second squared acceleration environment of Earth would be generated from an 800 kilogram equivalent weight. So if this man thinks he can stop a Honda Odyssey from taking off, he has to demonstrate he could hold an 800 kilogram weight up off the ground. Now you can see how easy it is to actually decide conditions from a provided force. You just lop a 0 off and you now have the equivalent mass. And now you can start thinking about the reality of the situation. Now, I want you to get familiar with this technique because it will make a huge difference to your comprehension of the situation. Let's try another example. Larry is a doofus you can't stand. Because I'm tired of all these teaching problems. It's like, Larry has a friend. No, this guy's an idiot. Nobody likes him. He's a smartass. He's showing off all the time, and he makes impossible statements. You guys go to a university engineering department, and they've set up a bunch of demonstrations for kids to try, and Larry's broke most of them. And one of the ones he gets out is a spring machine. And he claims when he pulled on the spring machine, he generated 17,500 newtons of pull. And you're like, no, you didn't. And he's like, I did. And you're like, you didn't. And he's like, I did. So you're like, okay, everybody, I'm going to prove that Larry could not possibly have pulled 17,500 newtons. You pretend that it was a mass suspended in gravity, what I call a mass equivalent to the force. You pretend that 17,500 newtons came from a hanging mass, and you get that Larry would be capable of lifting a 1,750 kilogram mass. That's like a Honda Civic fully loaded with passengers. There is no way anybody can do 1,750 kilograms in the history of Earth. Nobody has done that. But when I tell you it's 17,500 newtons, you're like, because you haven't worked with them much. So knock a zero off and instantly you understand the magnitude of that force, what it's really telling you.